come to the iron phase diagram. Okay, so iron is a single metal, a single element. So okay, so what is the purest metal phase diagram? I already made you know that if you are going to draw a phase diagram, then what you need first, you need a cooling curve of that particular alloy or the metal that you are concerned about. Okay, so as we are going to study the topic iron phase diagram, it means in the purest form, right? I hope you remember that we have discussed the second of the cooling curve. Yeah, this one. This cooling curve is for the purest one, pure element. This for the binary, this for the more than two phases, right? So three different cooling curve we have discussed. Okay, so in which this one, first one is for your pure metal, or purest metal, right? So if we talk about the iron phase diagram, that is about for the uh, pure metal, right? So the melting point of the iron is 1539 centigrade, 1539 degrees centigrade. So I mean, when you reach at this particular temperature, then iron will start melting. Okay, so iron is relatively soft and ductile material. The important allotropic forms of iron are alpha, beta, and gamma iron. So, I mean, alpha beta is not arbitrary here. It is the name of that particular allotropic. Allotropic means, I already made you know, the allotropic is the phases of the element or metals, okay, when they are having a different temperature. And it could be of the same phase, but they have the different crystal structures. Okay, so so these are the allotropes of alpha, beta, allotropes of iron are alpha, beta, and gamma. The experience of phases depends upon the temperature to which the iron is heated. Obviously, because these all are the games of heating or cooling. Both in the sense they are the concern of about the temperature. So if you are raising the temperature, it is heating, and if you are decreasing the temperature, means you are making them cool down, or it's a cooling process, right? So these all phases or these all different phase will exist only on when you are either cooling or you are it's just about the temperature which plays an important role. Okay, the figure below shows the cooling curve for the pure molten iron plotted in the time versus temperature coordinate. Okay, you see here on the x-axis we have a time, because how why we have taken the time, not to composition, because it's a pure metal. So we don't need to concern about the composition. It's a pure metal. And on y-axis we have kept temperature same as we were keeping. Okay. So now when molten metal when molten iron solidify from the liquid state at 15 and 1539, I mean 1539 degrees C, this transformation is accompanied by an evolution of heat, right? Obvious, if you are making them cool, then it would be the heat would be released from the system. This is represented by the horizontal line on the temperature curve at 1539 degrees C. For the considerable amount of time, the temperature remains steady at this point when the transformation of the liquid into the solid is complete. Okay, so as I already made you know, whenever the phase changes occur, the uh, temperature remains constant. Okay, so this is what. So first you are at having 1539 degrees C. It is the temperature of the melting point. Means if you will reduce the temperature of the molten iron, okay, then it will start changing into solids. Okay, so the phase change will occur, and as soon as the phase change will occur, you would be having the constant temperature. That's why it is having the constant or constant line. As you can see, this is your constant line. Temperature is not changing here till here, right? Why? Because this is the point at which this is a basically uh, melting point of iron. So if you are heating them, so till 1539 centigrade, you would be observed that all the heat is going to raise the temperature of iron. But as soon as you reach the 1539 degrees C, temperature, then your iron will or start melting. Okay, that is the melting point. And reverse of that, if you are having the liquid state of that particular iron and now you are cooling them, then it would be start it would be behaving like a phase changing once it reach at 1539 degrees C. So here it will start freezing means they will start to solidify themselves. Until its solidification will occur, it would be having the same temperature, or it is a constant temperature, which is known as your its melting point, which is 1539 of iron. Okay, so what next? When transformation of the liquid is complete, I mean, it means till here you have completed all the sorry. Okay, so when we reach at complete here the solidification complete. Okay, so now what? The iron in the beta form the BCC structure. Okay, so when the transformation of the solid liquid into solid is complete, the iron is in the form of beta form of BCC. So as you can see here, so this at this point, all this particular point, this here, it is a decreasing, right? At this point, you have all uh, the liquid converted into solid. Okay, the solid iron at this particular temperature is known as your beta iron. Okay, so beta iron, and they have what kind of the structure? BCC. BCC is body center, as you can see. This is the body center. You can see this is the temperature because once they are at this point, they have converted, they have that. So keep in mind, at this particular point, it is not having BCC structure, because at this particular point started converted into solid. But once it reached here, this is corresponding to the time. So this particular point shows that it has reached at the solidification point, making means they have converted into solid. So all the liquid got converted into solid. So that as soon as they just converted, that is the point where the solid iron is known as your what was the name? Beta iron. Okay, so beta iron, and here if we talk about the body crystal structure, then it has the BCC. BCC means body center cubic structure. So how they represent this like this. So you have a cube. Okay, and in cube, all of the atoms are presented at each corner, as you can see here. 3, 4, 5, 6, 7. This one is 8. And at the each corner you have only 1/8 part of a single atom, as I have already discussed these things in unit first. Okay, so uh, if we talk about the BCC, means a single atom, a complete atom is at the center of that cube, and each vertex is having 1/8 part of the single atom. Okay, so overall how many atoms are there in BCC? Only 2, because each 8 corners having the 1/8 part, so that would contribute to the total 1 atom only, and 1 atom is at the center, so that all will count as a 2 atoms in unit cell. Okay, this is your as soon as all the molten iron converted into solid, that solid is known as beta iron, and that is of crystal size. Crystals structure is of BCC, body centered cubic cell. Okay, now after some times, okay, the temperature falls to the 1404 degree. Okay, so as you are just cooling molten metal. Okay, so molten iron, basically here we are a specific element, which is iron. Okay, so if you are continuously reducing the temperature of that particular metal. So once you reach the 1404, 1404 degrees C, and there is evolution of the heat represented by the horizontal line. And at this point, this heat allows the temperature to remain steady. And here, the tropic modification of the iron takes place from beta to gamma FCC. So here, once you reach at the 1404, here the next phase change start. and whenever the phase change start, the temperature remains constant. Okay, so temperature of 1404 remain constant during the phase change, but they are still in the solid state. But where the phase changes are occurring, their crystal structure is being changed, and that is from beta to gamma. What the kind of the structure there is? It's a FCC. FCC means face centered cubic crystal. Face centered means, okay, so each corner will having the only 1/8 part of the atoms, and each faces means in cube we are having six faces. So each faces have 1/2, or you can say 50% of the atom is present. I mean 50% by volume fraction, or you can say 1/2 part of a single atom is present at single face. So there are total six faces in a cubic structure. So you are having total number of three atoms from face, or from faces, or and you have one atom from each corners. Okay, so total number of the atoms are four. In case of body center, you are having only two, but here we are having number of four atoms. Okay, as you can see. So whatever the temperature, whatever the heat that you have given to the system, okay, to make them sorry, whatever the heat that you have extracted from the system to make them cool, that is your sensible heat, and that sensible heat is showing by this particular line, this arrow. Okay, and once they have reached at this particular point, then it would be having this. As you can see, it is a constant temperature. This constant temperature shows that we are having we are having you know the phase change, because whenever the phase changes occurs, we don't see any changes in temperature. So temperature remains constant till here, and this changes occurs, okay, in their crystal structure, and that is known as the beta to gamma, and the gamma have the FCC means phase centered cubic structure, as you can see in this particular diagram. Okay, so at each corner say we have the atoms, and here is it's just showing the atoms, but 1/8 part of the atom is contributed to this particular cell. Okay, this is for the other one. So if we talk about just only the one unit cell, then each corner having only 1/8 part of unit. Sorry, atom. Okay, so and each phases have the 1/2 part of atom. Okay, so that will contribute to the total four atoms. We have discussed these all things in details in unit 1. I hope that you remember. Okay, so now if you will still extract the heat from the particular, you know, solid of iron, then you will reach at 901 degrees C. Once you reach at that 9 degrees C, then what you will be having? You would be having the different, which is known as gamma. Okay, gamma already we have done. Now we have delta maybe. So third is, yeah, alpha iron of BCC. The third temperature effect on the further cooling occurs at 910 degrees C. Here the gamma iron changes into alpha irons, okay, of BCC. So here we have the body center, as we have the first here, the body center, okay. But here we have the beta iron, okay. Though we have the same body crystal structure of BCC, but here it is the beta iron, here is the alpha iron, okay. So obvious here the phase changes occurs at 910 degree C, 910 degree C, that the would be of your phase change, and that would be of constant temperature. Okay, as you can see here, this particular line shows indicate the constant line. It means they are having a constant temperature, means they are changing their phase. Okay. Now this transformation is non-magnetic, whereas the earlier two transformations were paramagnetic in the nature, as you can see. Okay, so before we have the two combinations. If the first one is the beta BCC and gamma FCC. These two were of magnetic natures. They both were having the magnetic nature. Okay, as you know, what is a magnetic? Okay, magnet have the capacity of repulsion features, means they can attract and they can repel the iron. Okay, so magnet has this kind of capacity. Okay, so whatever the third point, I mean, at after 190 degree C, the phase changes occur, and that phase changes the alpha iron BCC. This is of nature. This is having the nature of non-magnetic nature. Okay. Though before that we have the two other allotropes, beta and gamma. They both have a magnetic nature. Okay. But alpha iron has, though they have the same BCC, but still they are of non-magnetic nature. Okay. The fourth one and the last allotrope changes occurs on the further cooling till the temperature 768 degrees C. You can see we can reduce and then we reach at 760 degrees C. Right. So what we get here is at an end corresponding to the alpha iron. Alpha iron here is slightly, highly magnetic and exists up to the room temperature. So when we reached at this particular temperature, which is 768, so here the phase changes also occur. And in this case, the same things remain the same. But what happens here, the magnetic features has incorporated. It means the during this particular things, you know, there is non-magnetic nature. But after that, it has a magnetic nature. Though they have the same BCC, okay, crystal structure is the same BCC, but their magnetic nature comes back. Okay, so they are alpha iron as well, but they are now in a magnetic nature. So in between the 910 to 768 degree, whatever the iron allotropes that we get, that are of having non-magnetic nature. But after that, once 768 degree C, you are having the magnet which have, sorry, you are getting the iron which have the magnetic nature. And till where, till the room temperature, after that, if you cool down to the room temperature, okay, this is of the same nature, means the magnetic nature. Only this particular region, the 910 degree C to 760 degree C, the allotrope of iron is of non-magnetic nature. Okay, so as you can see in this left side, they all are magnetic, and only in this region it is non-magnetic. Okay, so what is the region? Region of 910 degree C to 76 degree C, 768 degree C. Between these temperature, whatever the allotropes of iron that we get, that is of non-magnetic nature. Got it? Okay, so keep in mind, once you reach at 910, you are having the alpha iron of BCC nature. Okay, so if we talk about what the different kind of the structure that we get in the cooling curve of or the phase diagram of the iron, only two, either BCC or FCC, right? None of them, none other we get in iron. Okay, but what is the difference? That at the first, when it just solidify and convert into the solid, there we have the beta iron and having BCC nature. Okay, and if we talk about the then we come to the 1404. Here we have the gamma and iron. I mean the conversion of that iron is into beta to gamma. Okay, and that would be of BCC nature. Sorry, FCC nature. First of all, it's a BCC. Now convert into the FCC, and once you have crossed the 190, then you reach at 768 degree C, and here also the phase changes occur. Here you get the alpha region. Okay, so here you get also alpha. I mean, first one is the beta of BCC. Second, 1400, you get the gamma FCC, and third 910, you get again the BCC of but alpha iron. Okay, until 668, sorry, 768 degrees C, you are having the same nature of cubic crystal BCC and alpha iron, but what the changes is of the magnetic nature. Before that you were non-magnetic, and now you are having the magnetic. I hope that you are clear what this particular phase diagram means. Okay. So on y-axis you have the temperature, on x-axis you have a time. Okay, because it's a cooling curve that basically help us to draw a phase diagram, right? So on x-axis you have a time, okay, and time versus temperature gives you other different kind of phases of that particular iron, and that phases being drawn with the help of the cooling curve is known as your phase diagram. Okay, I hope that you are clear right now, right? And yeah, keep in mind throughout the phase diagram you have the magnetic nature of iron, except one, which is known as the temperature ranges from 910 degrees C to 768 degrees C. Okay, rest all you are having your magnetic nature. And after 910, you are having the same name, which is the alpha iron of same structure BCC, but the difference is since 910 to 6768 degrees C, you are having the non-magnetic nature, and after 768 degrees C to the room temperature, you are having your magnetic nature. Got it?